And as we know, everything physical starts with a material problem. And for most of industrial's history, solving it meant a very long and tedious trial and error process. Luckily, this is changing rather fast. And that puts us into the next session of today. Again, we have an array of speakers, 10 minutes each, and we are very fortunate enough to be guided through this conversation by our own moderator, who's none other than David Champagne, Senior Partner at McKinsey & Company. Ladies and gentlemen, put your hands together for David.
Excellent. Thank you for being here. The question I'll kick off today with is how we turn an impressive technology that is AI into an engine for materials innovation. That's useful. In materials-heavy industries, the bottleneck is rarely the lack of ideas. It's the cycle time from hypothesis to candidate to validated performance and then eventually scale up. So my argument today is about how AI changes that cycle, not replacing scientists, but helping them search wider, faster, and connect the benchtop to the top line. So to get started, it's useful to go to a warning from a previous technological revolution, that of IT systems in the 80s and early 90s, where we saw a paradox coined by Robert Solow. You could see the computer age everywhere except in the productivity statistics of the American economy. And that's a useful warning because many organizations today are spending heavily on AI, including in R&D, but enterprise-level productivity does not move automatically. Technology layered on top of old processes, as we've heard earlier, tends to produce local efficiency rather than system-level productivity. And in materials discovery, the paradox is especially acute. AI is already showing up in a bunch of places: literature, search tools, lab notebooks, property models. We've seen simulation, formulation, synthesis planning. But the hard metric is not how many models we deploy. It's whether we create better materials faster with a higher probability of success and lower cost. So today, the question will be, what has to change for AI to show up in productivity statistics and material discovery? And a couple things are changing today that are going to help, and they're happening all at once. So the materials foundation models are getting better. I mean, DeepMind's GNOME identified 2.2 million candidate crystal structures. 380,000 of them were stable. Doesn't mean that everyone is going to turn into a commercial material, but does change the size of the search space considerably. Second, the lab model itself is changing. So the A lab at Berkeley combined computation, machine learning, robotics, X-ray diffraction, active learning to synthesize 36 compounds in 17 days. So discovery is starting to look less like a linear process with a handoff at the end, but rather it's starting to look like a continuous learning system. So we like to separate two flavors of AI productivity, especially when we're talking with large corporates. There's a lot of focus on operational AI nowadays. If you look at AI strategies for most of the top companies out there, they'll touch on both operational and scientific, but really their investment is focused on operational. And this is about how do you run R&D more efficiently, how do you help with documentation, planning, quality, yield, regulatory work, routine analysis. It's valuable, and it's often the fastest path to measurable impact. But it's scientific AI that asks a different question around how we create new or better materials. And it works directly on molecules, polymers, crystals, formulations, properties, simulations, spectra, images, process data, and it improves shots on goal and the hit rate. So for materials discovery, operational AI is necessary, but it's not sufficient. The differentiating capability is scientific AI embedded in the discovery loop. So a useful way to think about the prize here is in the DMTA cycle, so design, make, test, and analyze. If AI helps you run that cycle twice as fast, with half as many experiments per launch, moving from lab to pilot with higher confidence candidates, and exploring 4 times as many targets, the impact will compound. And it's not magic, it's just math on a portfolio level. You have more credible candidates, faster feedback, fewer blind experiments, better translation to scale. And that's where the productivity doubles. This is a very typical aspiration for a large corporate in terms of R&D productivity. Let's try to double this thing in 2 years or so. Now, when we get deeper, foundation models are a critical aspect of the technology that's needed to power this, because they convert very messy scientific objects into pretty useful representations. So a material, a polymer, molecule, a reaction, a spectrum, an image, or even a scientific paper can be represented as an embedding, this long vector of digits that captures pattern learned from large data sets. And it's in that representation space on the right that we can ask new questions. Which candidate is similar to a high-performing known material? Which structure is likely to have the stability that we need? Which synthesis route looks feasible? And which untested region of the design space is most worth exploring? So the practical point here is not that the model knows the science in a human way. It gives scientists a computational map of a much larger discovery space that they could, versus what they could actually manually traverse. But of course, this is only a map, and it's only going to give you advantage if you connect it to experiments. That's where this is a simple but pretty core concept. We've heard some of this in the previous Bosch presentation. I mean, the operating model matters a lot when you're rewiring R&D, and the future model is not one of the AI on the side and the lab on the other. It's a closed loop between the two, where the models prioritize candidates, the labs make and test them, characterization data comes back, the model updates its beliefs, scientists redirect the next round. So that matters because materials data is often sparse, proprietary, noisy, it's tied to specific instruments and process conditions. So the public data that's available out there can start the engine, but it's really your proprietary experimental data that will create a moat around this. So winning organizations will not just have better algorithms, they'll have better learning loops, faster experiment design, better measurement, cleaner data capture, and governance that lets scientists trust and reuse the evidence. So we see that in a bunch of different places. We've heard of deep learning surrogates in physics just now. In physics-heavy engineering, the deep learning surrogates, they learn to approximate expensive simulations, and instead of spending days, as we heard, a full model can look at every design variant in a couple seconds. And it's not that you eliminate the needs for physics, it just makes physics more scalable. You still validate, you still use the high-fidelity model, but the exploration space gets much larger, and the expensive tools are used only when they matter the most. In chemistry, the pattern is inverse design. So instead of beginning with a known set of molecules and asking what they do, we start with the properties that we want, and we search for candidates that might deliver them. So one example from our work here was using a chemistry foundation model to help a mining company identify new reagents to extract metals from ore. And the models helped the chemists move towards molecules that had better properties, including some that had never been studied as reagents. And by the way, you can explore subsets of that space to make sure you have enough freedom to operate versus existing IP protection. So the impact was not just that AI invented, it wasn't about AI inventing completely new chemistry, but it expanded the solution space and guided the experts towards better bets, and these bets could be made much earlier and protected. So in biology, not going to spend a ton of time here, but that's where large pharmaceutical companies have invested a lot in the last 5 years. They go very multimodal. So that's an important concept here that has some learnings associated. So they combine images, molecular structures, omics, experimental readouts into a shared representation. So it's a concatenation of the embeddings to get a deeper, richer representation of different concepts, and they use that to nominate better hypotheses. The lessons here for materials is that the most powerful systems combine modalities rather than relying on a single data source. Multimodal beats single mode in instances where the science is very complex, which obviously biology definitely is. So to finish, we talk a little bit about the economic story here. The way we see it today, operational AI and some targeted scientific AI interventions produce real efficiency gains. There's faster analyses, fewer defects, lower energy, better experiments. But over the next 3 to 5 years, what we see is a bigger unlock that transforms R&D with faster throughput, lower cost per launch, and a much broader exploration. Beyond that, 5+ year, the upside will be a net new value with new materials that enable new industries, better batteries, lower carbon processes, more efficient semiconductors, and accelerated energy transition. So the call to action is pragmatic. Don't start with a giant AI transformation that claims to be able to revolutionize everything. Pick a few high-value domains in discovery, instrument the DMTA loop, connect the models to the experiments, and force value release every quarter. You need to be able to see impact every quarter. Building the data, the operating muscle will come incrementally as you go. If we do this, AI will show up where it matters the most, not in demos, but in the productivity of scientific discovery across industries. Thank you very much.
Okay, good afternoon, everyone. Happy to be here with you. When we think about deep tech, we usually think software, we think AI, we think chips. But what if we rethink and if material itself becomes the technology? So not just supporting innovation, but being the innovation. That's what I would like to talk about today. We call this smart matter. Materials are not longer passive. They are designed to sense the world around them, and that is happening now, steering at the level of thin film. For centuries, materials had one job. If you think about Romans building aqueducts, until today, it's mortar, it's stones, it's materials that have to be strong, they have to be reliable, and at the same time, they are completely passive. So if you touch them, if I touch the chair, the wall, nothing ever happens. And a wall is a wall, so there is no interaction, there is no feedback. The world we are building has fundamentally changed. What we need now is intuitive interfaces, human-machine interaction for robotics, intelligent environments. Materials have to evolve within their usage, and they need to sense, they need to adapt, and they need to interact with us or with other machines. At Wacker, we started at the smallest possible level, the material itself. These here, what you can see here, are ultra-thin silicon films. They are produced at industrial scale, roll to roll. And what makes them special is not just that they are a material, it's the precision that comes with these materials. And I have one example here with me. So this is the material. It's super flexible. You can print stuff on it, as you see, and I'll show you in a minute how that works. So the key capability is that you can have micrometer control that enables the sensing capability. So we have a layered system here with electrodes on it and non-functional layers, all basically printed into this very flexible material. So what happens when you press it? And I hope the video, it's pretty small. So you do get the signal, it does interact, the structure changes, and the electrical signal changes, and suddenly the material becomes a sensor and is more than just a material. Now, if you think what that enables, if you think about automotive interiors, touch screens, or more intuitive, they are lighter, they are way more flexible. You don't need glass surfaces anymore. Wearable sensors can follow human body and human body traction. In robotics, you have soft systems that can feel instead of just move around mechanically like robotic hands. So it's a completely different way of building systems. And sensing is just the beginning of it all. It can be connected, it can be integrated, and it can be pimped up with intelligence. So it's not just sensing, it's deciding and acting, and materials become the actual active part of that technology. So let me close with one thought. For decades, we've built intelligence into software, starting to build into the physical world. And now we are actually building that intelligence into the material itself. And the question is no longer, what can we build with materials, but what behavior do we want to build into the matter to integrate that and come to true integrated systems? Thank you for your attention.
Thank you. All right, thank you, Martina, for those insights. Now, our next titan applies AI materials or to material discovery at a molecular level. Ladies and gentlemen, please put your hands together for Alexander Hammer, co-founder and CEO of Dunia.
Thank you. Awesome. Yeah, thanks everyone. I'd like to talk about not just about smart materials, but like what if we could actually make materials programmable, make them programmable like software today. And maybe let's just start quickly. Why do materials matter so much, right? So not actually this far from here. I think it's like roughly 20, 25 kilometers. Bit more than 100 years ago, there was a man called Fritz Haber who did a lot of experiments, very trial and error, to invent what ultimately became known as the Haber-Bosch process. Right? So it's like one material. There were 3 Nobel Prizes awarded for it, and every second nitrogen atom in your bodies actually came through that one chemical process. So materials can really, really matter. In order to achieve that, it actually took over 20,000 of experiments that was a massive effort by a chemist called Alvin Mittag and his team, and years of trial and error to really find a scalable process. And that's, I guess, how materials, in a way, are still being developed today. So what if we could compress the timeline using AI, using technology? I think I really like this example so much because, in a way, it just reminds us that like a lot of materials are actually being discovered and not designed. Today, like how this came about was first there was a Nobel Prize for the discovery of this process. There was a second Nobel Prize for actually industrializing it, bringing it to commercial scale. And then 80 years passed until there was a third Nobel Prize awarded, actually also here in Berlin, for Gerhard Ertl, for actually understanding the mechanisms that were behind that process. It turns out, just last year, there was another paper that might question, like, do we really understand how this mechanism works? Maybe not. Right? So far, understanding came after, industrialization came first, and discovery sort of is where it always starts. And it's all serendipitous, right? Like serendipity plays such a big role in sciences. So what if we could actually truly start designing materials? And this is not a new idea. This is like a quote from Iron Man 2 back in 2010. There was already an AI called Jarvis, right? And this is an actual dialogue there. There's a proposed material to kind of solve a big challenge, and there could be a viable replacement for palladium. Unfortunately, it is impossible to synthesize. So that's like a direct quote, and then afterwards, Iron Man is very sad. So why can't we do this yet? Or like this is a bit like even AI in 2026 can propose already, as we heard, like millions of new materials, but like we don't quite know how to make them. And even when we make them, there still is this sim to real gap. Simulations tell you one thing. The reality is more complex, right? Any real material is always part of a system. How these materials actually behave in these real operating environments, these models, they don't quite know just yet. And that has to do with a lot of these models or the simulations we're using today, they're based on very idealized simulations, right? We're talking about an approximation of an ideal system. And then the real world is just a lot more messy than that, right? We have defects, we have boundaries, we have disorder, we have multi-phase systems. So an emerging technology, and I think that was already referenced in one of the previous talks, is being truly able to connect, to translate these bits to atoms in its most literal way using this new technology called autonomous labs. It's basically helping to bridge the gap between the digital world and the physical world, connecting AI with these physical systems. And the way to think about it, or the way I think about it, is that thanks to machine learning, already today, and this is one of the most exciting advancements, I think, is that we are able to run more realistic simulations. We're able to actually look at materials and look at expanded time spans, looking at larger systems, and I think this is a massive advance that's already working today. So there's some real productivity gains already today. If you're a computational researcher, this just works. If you're coming from the manufacturing side, you don't quite know what to do with that. It's not actually that helpful. So then you have to think about, okay, how can we qualify materials in industrial conditions? How we can make sure that this manufacturing actually is scalable? How do we make sure that synthesis can actually be scaled up? And I think this AI-driven autonomous labs is really how you bring those two worlds together, right? You can design those for manufacturing. You can actually understand how to make those materials, and you can have AI essentially driving those. So in essence, I guess what I'm saying is that all of the tools have become available, and they've really had massive advances on both simulations and also this real-world side. But so far, there was a missing interface, and this is essentially what our company, Dunya, has been building. This is a photo of our lab. It's actually here in Berlin, in Adlershof, close to the airport, so if you have to fly out, feel free to connect. Maybe you can arrange a visit. But this is really a way how you can bridge this gap. And this is essentially Dunya building the digital to physical transformer, right? So the same way you have a diffusion model and you have a prompt and you get an image out, what if we were able to have this digital specification of the material that you want and you actually get a physical material in your hands? So this is essentially the system we've been building end to end using three core components. It's a scientific reasoning agent that essentially comes up with a new idea, a new suggestion, using all of the prior knowledge we have, all of the information available, and it's giving us an actionable hypothesis, right? And then we send it to this API of this automated laboratory. The little asterisk, there's a lot of work there, right? There's a lot of details that go into that. But the idea there is that you can basically directly test it, you feed it back, and this is the classic loop, but it's fully digital. Everything gets captured in one central database. The part that's then really exciting is actually in this process, you generate so much data. And you heard it earlier as well, it's not any specific small little performance metric. We're looking really at multimodal data sets that can become really large, that are very rich in information. And this is what we can use then to train a world model, a materials world model that actually really understands how do materials behave, how do they actually change in operating conditions. And essentially what we see is that this approach already outperforms other methods that are currently being deployed, right? Looking at a lot of these atomistic foundation models, they're trained on these idealized simulations. They don't quite work for real-world problems. What you're seeing here is material degradation. It's the number one question anybody in industry will ever ask. Okay, you have a great material, is it actually stable, right? These models that are developed by Meta or Microsoft, they don't quite capture that. LLMs, for me, it's always magic. They actually work surprisingly well, but that it works at all is always phenomenal. And yet, they have no grounding in materials physics. So by actually using this multimodal data, like Dunya, we've been able to show that we truly converge on reality, that we learn how materials are made and how they actually behave in real systems. And in our hands, that already led to the first discoveries, which is quite exciting. So here we're looking at an example, which is an anode material, like an electrocoating, right? We're looking at an electrocatalyst ink. And what we did here is basically we ran a campaign with, of course, a lot of simulation, but then also in the real world made 450 new materials and all the way went to the device level to test them in a real operating setup. It took us 2 months to do. In the process, we rediscovered 100 years worth of research, including the commercial state-of-the-art, including patents that BASF filed just 2 years ago. And on top of that, we actually found a whole new chemical space. So this is a really special setup where we're talking about a novel discovery that is drop-in manufacturable using existing methods and actually has beyond the state-of-the-art performance. So when we showed that to our collaborators at Mateco, they said, okay, this effort alone would have taken us 4 years to do. Like, we're simply not set up to do this type of work. And they also told us, we wouldn't have come up to think there. Like, we wouldn't have thought to actually try this chemical space. It's unintuitive. This is just what we've been able to do recently. Now with agents, you can push it even one step further. So where other classical optimizers have essentially converged on the Pareto front on some optimal systems, by using context and reasoning, we were able to actually find new chemical space that even pushes that further, right? So this kind of shows the power of AI. And we presented the work recently at a conference. Feel free to come over to me. But this is, I think, we're one of the first companies that actually were able to show this, right? We're able to show that, using this, you can even get another step change. So where this is going is essentially Dunya's Giga Lab, right? This is our vision of where to go next. We will need factories that do science, right? We're at the very, very early days still of what will be, a scaling law. We've seen that in LLMs, what scale can do to these algorithms. So here we're talking about a 50,000 square meter facility that's essentially connecting AI with the physical world, with state-of-the-art automation, generating terabytes of data, hundreds of billions of training tokens, to then really launch these foundation models that really help us understand the real world. And that's centered around critical innovation domains here in Europe, here for 4 different challenges across thin films, across coatings, formulations, batteries. And we believe we can actually build a system so powerful that we could discover new material every 30 days, right? And then really unlock these frontier technologies. There could be new batteries for flying cars. It could be superconducting magnets for fusion, smart glasses. Mark Zuckerberg is very passionate about those. All of that is bottlenecked by materials today, and we think using this technology, we might be able to just unlock that. So yeah, thank you so much. This was my talk. And yeah.
Thank you, Alex. Yes, I will grab that from you. And new material every 30 days. Wow, that's quite ambitious. Best of luck to exactly that. We're going to move on to our next titan, who sits at the intersection of quantum computing and material science. Ladies and gentlemen, please put your hands together for Toby Kubert, co-founder, CTO, and CSCIO at Phasecraft.
Okay. Thanks for being here. So Phasecraft is the quantum algorithms company. It was founded by myself, Ashley Montanaro, John Morton, about 5-6 years ago. We have offices in London, Bristol, Washington, DC. And we founded Phasecraft to get real-world algorithms solving real-world applications problems onto quantum hardware that actually exists today or tomorrow, not in 10 or 20 years' time. Now, we've all heard about the promise of quantum computing, how quantum computers could help us design new materials, discover new drugs, solve incredibly challenging problems in the blink of the eye. But anyone who's read beyond the hype knows that there are a lot of challenges in quantum computing. Current quantum computers are plagued by noise and errors. We know in principle how to solve this. We know how to do, theoretically, error correction, fault-tolerant quantum computing that would combat these errors. But the number of qubits you would need to do fault-tolerant quantum computing runs in the order of millions. And today's quantum computers have just a few hundred qubits, and they only can do a few thousand instructions before their noise just wipes out all of your quantum data. So in many ways, it feels like a deep tech momentum, like we're all living in the future. But personally, I often feel like I'm living in the 1950s. So because this is what it was like during the early days of classical computers, when you had massive machines built to solve really difficult, complex problems, pushing the limits of what was possible physically. This isn't a picture of a quantum computer. It looks like a dilution refrigerator. It's actually a memory unit, a photo of the memory unit from the UNIVAC, which is one of the first computers to store data electronically. It stored it in sound waves in tubes of liquid mercury. This was actually the first computer to ever use to predict the winner of an American election, and it actually got the result right, but the people who built the UNIVAC didn't believe the result of their computation until the results came in and they saw that Eisenhower had won in a landslide that surprised everyone. But revolutions in computer history, they're often thought to follow from breakthroughs in physical hardware. But what's often overlooked is the fact that the hardware was developing at the same time as or even sometimes long after the algorithms that ran on that hardware were invented and developed. So the predecessor to the UNIVAC was the ENIAC computer, built in 1948. It did nuclear physics simulations, simulated nuclear reactions. But this application would have been completely impossible if it wasn't for John von Neumann and Nicholas Metropolis, who nearly 10 years earlier had invented the Metropolis algorithm. Going a step backwards, the computer that broke the Enigma code in 1940, it was only able to do that because of an algorithm invented by Alan Turing in 1939. So when we come back to the day, the analogy is very clear. We should be putting as much resource and effort into developing the algorithms that run and solve real-world problems on quantum computers as we put into developing the hardware. And this is what we do at Phasecraft. We're a pure-play quantum algorithms company. We're developing and optimizing the algorithms that will shape the next chapter of computing alongside and in partnership with the leading hardware providers who are building the hardware that's this crazy, incredible quantum hardware that can compute in this new way. So to understand how we do this at Phasecraft, let's look at a typical problem of materials science, which is materials modeling is one of a number of very promising applications of this sort of future computing platform. So this is strontium vanadate. It's a potential component of next-generation solar cells, batteries. It's a classic example where industry-standard methods based on density functional theory fail. They fail for well-known, understood reasons because they don't manage to capture the electron correlation effects in this material that play an important role in its material properties. And based on the best algorithms known at the time Phasecraft was founded, quantum computers are very good at simulating quantum mechanics. But the best algorithms when we founded the company would estimated to need hundreds of billions of operations to do an ab initio model of this material. And remember, today's best quantum hardware doesn't have 100 billions of operations. It can do about a few thousand before it falls over. So this looks completely intractable, not just today's quantum computers, but even to quantum computers that might exist in 10 or 20 years' time. So how might we try and make this problem less intractable? Well, you can look at an example of a quantum algorithm. We still today write quantum algorithms in terms of individual quantum logic gates. They look, written out. They look like you see diagrams like this. And you might hope to optimize this circuit a bit. Maybe you can reduce, redundant gates and collapse things, and maybe you can even automate this in a quantum compiler. And if you do all of this, maybe you manage to reduce, a factor of 2. Reduce this, get it down by multiplying by a half. So this is still completely intractable. So to solve important problems on today's or even tomorrow's quantum computers, we needed to make a much more radical improvements to the algorithms themselves. Throw away the textbooks and think again. We developed a novel approach in Phasecraft to the materials modeling on quantum computers, which combines new ideas ranging from condensed matter theory through to quantum information theory, through to quantum algorithm design. And we implemented this in a pipeline that takes a description of a material unit cell, and then it automates all of this process of turning this into an extremely efficient, optimized quantum circuit for simulating ab initio simulations of that material. And that's what allowed us to reduce the cost of modeling strontium vanadate by a factor of over 43 million. So in just a few short years, Phasecraft took a problem that was believed to be completely intractable even for quantum computers in the 2040s, within touching distance of today's quantum computers. And this isn't just one algorithm for a single material. This is an entire process that we have run through our pipeline, nearly 50 different materials, crystalline materials that are interesting in potential industrial applications. You can find all of these on our website. If you look at materials.phasecraft.io, you'll find all of the details. So if you make a 43 million X return for your investors as a startup, they are extremely happy. If you make a 43 million X improvement on a quantum algorithm, unfortunately, it's not enough. This is still not enough to get this stuff to run on quantum computers that exist or are likely to exist for the next few years. So we took a step back, and we thought, how can we approach this from a radically different perspective? How can we take advantage of the amazing work that's already been done in the materials modeling community over many, many decades? As it turns out, sometimes the best quantum algorithms don't actually use quantum computing at all. So density functional theory is the state of the art for finding ground states, band structures, band gaps of materials in industry. It's a beautiful theoretical technique. The work in the 1970s by Cohn and Sham won a Nobel Prize for them in the late 1990s for making this a practical computational method. And the reality is that this classical conventional approach is pretty good at solving most of the problem. It just struggles with one small piece of it. It struggles to capture, for certain materials, certain molecules, not all, the effect of electron-electron interactions. It does very well on all the rest. And so what we thought is, can we just use a quantum computer to solve that difficult core of the problem and use density functional theory and standard classical workflows to do the heavy lifting on all of the rest of it? And so indeed, that's what we did. And the results have been very impressive. So the team, based on an idea I had a few years ago, the team developed this into a quantum-enhanced density functional theory algorithm. So this is a quick example of doing this on a very simple system. This is a 1D Hubbard model. Conventional vanilla DFT just doesn't capture the Mott physics of this. If you use bespoke, enhanced classical methods, you can, because it's 1D, you can actually solve this problem and know what the real solution should look like. It should have these shoulders here. And they're not captured by just sort of vanilla DFT. You have to work hard to get these. We took just vanilla DFT on a quantum computer that is 2 generations ago and 4 years ago, this data, on Google's predecessor of the current hardware. And just use this to enhance just vanilla DFT, and you recover the correct physics. And this is with real quantum hardware data that's extremely noisy, error-prone, and 4 years old. So to get out the most out of quantum computers, we need to figure out the algorithms that can run on the hardware that exists today or tomorrow, not the hardware that might exist on 1 and 2 decades' times. And for applications like materials modeling and helping with materials discovery, doing accurate ab initio simulations, the algorithms are critical if this is going to actually succeed. So the algorithms are force multiplier for the power of the hardware. They let you do more with less. And getting to quantum advantage in 3 years instead of 10 is very intellectually interesting, but it also has a whole load of practical applications. It means quantum computers actually starting to help discover novel battery materials this decade instead of next decade. For doing ab initio simulations of interesting target models for drug discovery next decade, not in 2 decades' time. And in other domains, similar mathematics and techniques applied to combinatorial optimization problems, allow things like using quantum computers to help design more efficient, robust energy networks. We can't do this without the hardware, and we are fortunate and unique. I think we're the only people in the world that are running on all of the world's biggest and best quantum computers. We're running on Google's hardware. We're working with Rigetti, with IBM on the superconducting circuit hardware. We're also running on Quira's Rydberg atom array hardware, on Quantinuum's ion traps. I think we're the only people in the world with access to all of the world's best quantum computers. So I focus what can be done now and in the near future, but when fully scalable, fault-tolerant, error-corrected quantum hardware arrives, our techniques allow us to solve problems that are 43 million times bigger than anyone else can. And I can guarantee that we will never stop caring about a 43 million-fold efficiency improvement in algorithms. We still care about this level of improvement today in classical computing. So we need the quantum hardware to develop and continue to make progress. We also need the algorithms that will unlock that hardware for real-world practical applications. Thanks a lot for listening.
Thank you, Toby. And as someone who runs a hard tech innovation hub for early stage technologies, that certainly was something that resonated. All right, for our final titan in this session, I'd like us to put our hands together for someone who's putting the commercial layer on top of the science. Ladies and gentlemen, please welcome Yun Lo, CEO and co-founder of Rossi.
Thank you. I'm very sorry. I've been so absorbed by the presentations, I forgot mine completely. So actually, I'm extremely delighted when I was listening to all the other presentations, because it's a fantastic description of our technology world with these layered cakes. And all under the last layer, actually, it's the raw materials. We talk about quantum computing, we talk about AI, or the hardware. There are 2 very important materials. That's silicon and the silver. So silicon with transistors, semiconductors, and the silver is actually the only fantastic metal that has extraordinary electric and thermal conductivity for all the functions to be realized. So that explains the name of Rossi. When we started, so I'm from not a very young startup company from France, so return of silicon. So we are engaged in the recycling of old end-of-life photovoltaic modules to get all the high purity raw materials out from the modules. I have samples here. So there's silicon, silver, copper, glass, and aluminum. So the two most important materials, they are silicon and silver. So when we start the company, we call it return of silicon. Our heart is on silicon, the core material for PV, and actually can also be read as return of silver. Next step. Yeah, so I'm by education, I'm a physicist of quantum mechanics, so this enjoyed especially the other presentations. This also defines why from the first day of Rosie, my heart is on the high quality, high purity recycling to get these high purity raw materials out from end-of-life PV modules. So today, proudly, after 7-8 years development, so Rosie is the only company in the world we benchmark the same purity in the recycled materials, so whole panel of recycled materials, as when they are in the PV modules. And we are the only one who also close the industrial value chain of recycling and the reintegration in the strategic industry, so commercial reintegration, commercial circular economy in Europe. So this presentation was not done by AI, but I always start with a little history. I always look back, even we still have to go forward for many, many years. So the Rosie is an 8-year-old startup company. Our development roadmap is actually a perfect demonstration of how public funding, private investment, and also industrialization carried by industrial partners, how they managed to help us to move to here today. So you can see from the companies or investment fund on the cap table, we have industrial investors, we have a lot of public fund, and we also have the private fund. And because we are very limited in resources at the beginning of the company, this is actually, besides working with a team with a lot of young people, by the way, 40% of women in my engineering team, we were probably one of the first startup companies we used the AI for the upscaling. So the first 3-4 years, as a very classic European deep tech company, we devoted all the time for proof of technology, on the purity, quality, and also on the reintegration with key industrial players back to the value chain. So in the laboratory, after 3-4 years, laboratory development, we were already fully on the market to participate in all the tender calls in Europe to recycle on large scale for European market. And for that need, we need to upscale 100 times. We didn't have resources, so we were running AI to run this process upscaling of 100 times, which is actually realizing our first fully running operational factory today in Grenoble. And I'm going to show you some pictures later. So we all understand actually the photovoltaic actually offers a fantastic energy source since quite some years in Europe. And these modules, when they generate electricity, there's almost no CO2 footprint. However, during the manufacturing, many materials, they are very, very intensive on energy and CO2. And they consume actually a large quantity of resources from the world. For example, silver, we very often overlook this metal. So photovoltaic industry actually in the world, they consume more than 20% of worldwide silver, and very little is recycled. So recycling of all these raw materials locally, when I say locally, in Europe, recycle for Europe, in China, recycle for China, in US, recycle for US, actually reinforce the independence and sovereignty of every continent, and we do believe it's absolutely beneficial for the peace of the world. So, again, here's a comparison on how the raw materials look like after they recycle. As a team, is very much composed of chemists and physicists. So we were very careful in the design of the process that we don't touch the interior of the materials in order to keep their morphology and also their purity as they are in the PV modules. The idea is actually very simple because the purification, the manufacturing of every of these raw materials implies a very long value chain. So if we manage to keep high quality for the reintegration to different industry, we can actually shorten a lot this reintegration value chain that will make a lot of economic benefit and also environmental impact. So this is how the process is actually designed. So we're really quite proud that we managed that, showing the laboratory, showing the first factory, and show our expansion plan around Europe. I think most of you probably already hear now there's a tsunami of old PV modules that is coming with a lot of raw materials, with a lot of quality and value inside. We're not always explained. Today, a big part of PV modules, they're shredded, actually landfilled. So when we talk about the value in this tsunami of end-of-life PV modules, actually, the hypothesis is if we manage to get the high purity, the materials out of the PV modules in their proper purity, in their proper value. And we do believe that can only be done by technology, by process, and also by the realization of this technology and operation of these manufacturing sites. This is what we are working on in Roissy. So this is a glance of how the factory looks like. They are more than 100 times bigger as the first scaling up step. After laboratory process, which is a commercially running site today, serving the French market, serving the Swiss market, also receive panels from UK and Luxembourg, because this is the only site in Europe that can recycle the raw materials at highest purity. So we're quite happy that with very limited resources, with the help of AI, machine learning, and simulation, we could make a very big jump of 100 times in the construction of the factory. And this high purity in the raw material, that gives a very high margin for this business when the production is stabilized, when we can introduce well-regulated AI-aided operation. So you will reach a EBIT margin more than 50%, which is extraordinary for recycling. So our vision is very clear that this technology will be accelerated to cover different countries and different continents. So our vision in Europe is to establish a platform of high purity raw materials from recycling from different countries, have these pillars in order to manage these recycled materials and re-inject them back to different strategic industries. Well, I think that brings me to the end of the presentation.
Thank you, Yun. That's been fantastic. Now, does anyone here want to see firsthand the samples that you've brought with us? I think please head to her straight afterwards.
Thank you.